Welcome back, grade 10s. In today's lesson, we're going to continue with our discussion of the atom. Now, in the last lesson, we finished off by discussing isotopes. Now, when it comes to isotopes, we are very much focused on the nucleus of the atom. The nucleus of the atom contains the protons. Recall that the number of protons is what gives a specific element its identity. And because there are different isotopes of each element, different elements will contain a different number of neutrons, even if it's an element of the same type. But again, we were focused on the nucleus of the atom. And what we're going to move on to now is the electron configuration. So now we're zooming out of the nucleus and we're looking at how the electrons are arranged around the nucleus of an atom. So we've discussed the protons and the neutrons that make up the nucleus of an atom. Let's understand the arrangement of electrons in an atom. Let's discuss the light spectrum and visible light. A beam of white light is actually made up of the 7 colors of the rainbow. So when we refract a beam of white light, that means refraction means bending of light. So when we cause the white light to bend, specifically through a triangular prism or an object where the two ends are not parallel to each other, we get a refraction of light within the prism and another refraction of light as the light exits the prism. What's important here is that the white light breaks into the different colors of the rainbow. That's red, orange, yellow, green, blue, indigo, and violet. Red light has the lowest energy of all the visible light waves, and violet light has the highest energy of all the visible light waves. Now, this is called a continuous spectrum because it contains all 7 colors of the rainbow in their order. So if we go through these colors from red to violet with no gaps in between, that is called a continuous spectrum. Now, the light spectrum occurs because the different frequencies of light, when they enter glass, different frequencies travel slower than others. So, like I mentioned, red is the lowest energy light wave of the visible light waves, and it travels the slowest, and violet is the highest energy, and it travels the fastest. So, what we're seeing is the white light breaking into the different frequencies of color that make up the white. And because the different frequencies of light travel at different speeds through glass, then we get to see a continuous light spectrum on the other side of the prism. So when the white light enters the prism, it separates slightly into the 7 colors of the rainbow within the prism. And when it exits the prism, then the separation becomes greater. And the different colored lights bend at different angles, as already mentioned, as long as the prism surfaces where the light is going in and coming out are not parallel to one another. If this is confusing, then it makes sense to recap the section in waves on electromagnetic radiation. This is a useful video on light prisms, and I will include the link in the description. In 1913, Niels Bohr, a Danish scientist, produced a model, and he suggested that electrons move around an atom in specific energy levels, and each energy level is associated with a specific or fixed amount of energy. So what he means by that is this is the nucleus, and over here there is the first energy level. Now this electron lives in this first energy level, and in order to move up onto the next energy level, that electron needs to absorb a fixed amount of energy to get there. Now, when that electron loses energy and it moves back down to its original energy level, and we call that the ground state of the electron, and then it is going to release that energy in the form of light energy. Remember that energy cannot be created or destroyed. It can only be converted into other forms. So an atom that's absorbed energy, say heat energy or electrical energy, and has had the ability to jump up onto the next energy level, well, when it loses that excited state and wants to go back to its ground state, that energy needs to be converted into other forms of energy. It can't just disappear, and that energy gets converted into light energy. Now, every element has a different set of electrons in different energy levels. Therefore, different elements are associated with the release of different colors when they are heated or excited. So, for example, when an electric current is passed through hydrogen gas, that electric current provides the electrons with energy to jump up an energy level. And when those electrons lose that energy, then we find that the hydrogen gas emits a pink light. Now, what Niels Bohr did was he passed that light through a triangular prism. Remember that if you pass white light through a triangular prism, it will separate into the 7 colors of the rainbow. Now, in this case, Niels Bohr wanted to know what wavelengths of light make up this pink light emission of excited hydrogen. Now, this over here is called a non-continuous spectrum. And it's a non-continuous spectrum because it doesn't contain all the colors of the rainbow. So it doesn't have red, orange, yellow, green, blue, indigo, violet. It just has red and then a frequency of green and blue and violet. Hence, this is a non-continuous spectrum. So the hydrogen gas is energized. That hydrogen gas releases a light that Niels Bohr then passed through a prism, and he could then identify what specific frequencies of light make up this pink light that's emitted by hydrogen gas. The light, the color corresponds to the energy lost as the electrons move back down energy levels. Remember that when the electrons move back down to their original energy level, they release that energy as light. Now in grade 9, you would have learned about flame tests. So, for example, when we burn copper in oxygen, it produces a greenish colored flame. Now, a flame test is a procedure that's used in chemistry to identify the presence of certain elements based on the flame color and the emission spectrum that's produced through this flame color. By emission spectrum, we mean we allow that color to move through a prism and we figure out exactly what wavelengths of visible light make up this color. And that helps us to identify the presence of certain elements. So, for example, when group 1 metals react with oxygen, group 1 elements are highly reactive, so they burn very easily and very readily, and they produce brightly colored flames, and they produce metal oxide. So, for example, copper plus oxygen will make copper oxide. Copper oxide is a type of metal oxide. Zinc plus oxygen will form zinc oxide. That is a type of metal oxide. So lithium burns in oxygen to create a red flame, and sodium burns in oxygen to create an orange flame, and potassium burns in oxygen to create a lilac flame. And again, these colors help us to identify the presence of certain elements in a sample. But the key thing that we need to take from this is that when electrons gain energy, they get excited and they jump onto a higher energy level. That higher energy level is always going to be further away from the nucleus. And when that electron loses the energy that excited it, it moves back down to its original energy level, the ground state, and it releases that energy in the form of light. Each element has its own unique number of electrons and energy levels within which those electrons live. So each element emits its own characteristic flame color. Now that brings us to energy quantization. Because remember that when Bohr conducted his experiments on hydrogen, he said that the electrons need a set amount of energy to move up onto the next energy level. And that's where quantization comes in. So he proposed that the energy of the electrons in the hydrogen atoms, and in fact in any atom, is quantized. So an electron needs a fixed amount of energy to jump onto the next energy level. Let's take a look at this picture over here. We have an electron sitting in the first energy level. Now, if it gets excited, it has the potential to jump onto the next energy level. But it needs to absorb 13.1 electron volts, which is a very small unit of energy. So let's just say 13.1 units of energy to jump onto the next level. If it only absorbs 13 units of energy, it will stay put in its energy level. So it won't go up to the next step. It won't sit somewhere in between. It needs a fixed amount of energy, at the very least, to get to the next energy level. And so that is the quantum of energy. 13.1 electron volts is the quantum of energy that a hydrogen electron requires to jump onto the next energy level. So think about it like climbing a step. If you don't have enough energy to get onto the next step, you can't end up somewhere in the middle. It's the same idea here. If you're climbing the stairs and you don't have enough energy to get onto the next one, then you're going to be stuck on the previous step. Niels Bohr suggested that the electron in a hydrogen atom can only move from energy level to the next by absorbing or emitting fixed quanta of energy. Quanta are tiny but distinct quantities or pockets of energy. The singular of quanta is a quantum. So quanta are small amounts of energy, but they're set amounts of energy with a value associated to them. Keep in mind that what we're learning now is very confusing to conceptualize, and we have to use a lot of imagination. So using visual aids is very useful. I find this video to be very useful on helping us to understand the way that electrons move up and down energy levels, and I will include this link in the description. Now, I keep talking about these energy levels, but what are energy levels? Well, the electrons that surround an atom are found in regions around the nucleus, and those regions are called energy levels. Remember that an energy level is a three-dimensional space because an atom looks like a ball. So the energy levels, which is really areas surrounding the nucleus where we're most likely to find an electron. Those areas are three-dimensional. Electrons in different energy levels have different amounts of energy associated with them. The lowest energy level is the one closest to the nucleus. So we call that simply n equals 1. N equals 1 represent the energy level that is closest to the nucleus of an atom, and that is associated with less energy than the second energy level, which we refer to as n equals 2. And each energy level, there are 7 of them, potential 7 energy levels. Each energy level is associated with more and more energy relative to the previous energy level. The first energy level is the one that's closest to the nucleus, and it can hold fewer electrons, and the electrons that it holds have lower energies, and this is relative to higher energy levels. So the first energy level, which is the energy level, remember it's a three-dimensional space around the nucleus of an atom. The first energy level is the closest to the nucleus of the atom, and it can hold a maximum of 2 electrons. The second energy level can hold a maximum of 8 electrons. The third energy level can hold a maximum of 8 electrons, just like the second energy level. The fourth energy level can hold a maximum of 18 electrons. The fifth energy level can also hold a maximum of 18 electrons. The sixth energy level can hold a maximum of 32 electrons, and the seventh energy level can also hold a maximum of 32 electrons. So let's see how that relates to the periodic table. Remember that in the periodic table we have the rows. We have 7 rows, which are known as periods. So here we've got period 1, period 2, period 3, period 4, period 5, period 6, and period 7. I want you to just note that period 6 starts at element number 55, 56, 57, then it jumps straight to 72. So where's 58? 58 exists down here, all the way to 71. These elements over here actually fit into here and form part of period number 6. Then if we look at period 7, we've got element 87, 88, 89, and then we've got elements 90. A full periodic table will go all the way to element 118. Okay, so what I want you to take from that is that these elements over here are part of period 6, and these elements over here are part of period 7, but on the whole, we don't really work with these. Now, what we said is that there are 7 energy levels. Over here, we've got the elements of period 1. And elements of period 1 have their outermost electrons in the first energy level, which is n equals 1. Elements of period 2 have their outermost electrons in the second energy level, which is n equals 2. Period 3 elements have their outermost electrons in the third energy level, which is n equals 3. Period 4 elements have their outermost electrons in the fourth energy level, which is n equals 4. Period 5 elements have their outermost electrons in the fifth energy level, so that is n equals 5. Period 6 elements have their outermost electrons in the sixth energy level, and period 7 elements have their outermost electrons in the seventh energy level. What I'm going to show you next is that the energy level in this case n equals 1, which we said can hold a maximum of 2 electrons, that number 2 will correspond to the number of elements in that period. How many elements do we have in period 1? We have 2 elements. We have hydrogen and helium. The first energy level can hold a maximum of 2 electrons, which corresponds to the number of elements in that period. Let's look at n equals 2. Well, we said that n equals 2 can hold a maximum of 8 electrons. Now, if we're going to count the number of elements in period 2 from lithium to neon, there are 8 of them. We also said that n equals 3 can hold up to 8 electrons. And if we count the number of elements in the third energy level, there are 8 elements. N equals 4. We said that the fourth energy level can hold a maximum of 18 electrons. And if we count from potassium K, which is element number 19, to Kr, krypton, which is element 36, there are 18 different elements, and that corresponds to the 18 electrons that can be held by the fourth energy level. N equals 5 also can hold a maximum of 18 electrons, and that corresponds to the number of elements in period 5. Now, if we look at period 6, all of its outermost electrons will exist in the 6th energy level. And we said that there's a total of 32 electrons that can be held by the 6th energy level. And if we count from element 55 all the way to element 86, that will correspond to 32. And this is an incomplete periodic table. So we don't have all the way to element number 118, but a complete periodic table will contain all elements up to element 118. Remember that we said that the 7th energy level can also hold 32 electrons. So we have 32 elements in the 7th period, going from francium all the way to element number 118. So if we add up all these numbers, what number are we going to derive and what does it correspond to? Well, as I've just shown you, if we add up the 2 and the 8 and the 8 and the 18 and the 18 and the 32 and the 32, we reach 118, which corresponds to the total number of elements that exist in the periodic table. What I want to make clear to you up front is that we are only going to consider the first 4 energy levels. We are not going to consider n equals 5, 6, and 7. Also, we are only going to consider the very starting part of the 4th energy level. So we're not going to consider the full 4th energy level. So the first energy level can hold up to 2 electrons. The second energy level can hold up to 8. The third energy level can hold up to 8. The fourth energy level can hold up to 18. But we're only going to be concerned with the first 2 electrons that it can hold. I'd also like to make it clear that the nucleus sits somewhere inside this pink circle over here. Remember, the nucleus is very, very small relative to the size of the electron orbitals. Now we need to understand that each energy level is also made up of shells. So if we're going to zoom into n equals 1, we need to understand the shell structure of n equals 1. We're also going to zoom into n equals 2 and into n equals 3 and into the beginning part of n equals 4 and see what kind of shells exist in those energy levels. Now, the shells are really just different shapes that correspond to areas of high probability of finding an electron. In the first energy level, there's an S shell. In the second energy level and in the third energy level, there is an S and a P shell. In the fourth energy level, there's also a D shell, but we're only going to be looking at the S shell of the fourth energy level. So we're only concerned with S and P shells. D and F shells also exist, and I will explain to you which elements hold those D and F shells, but we are not going to work with D and F shells. We're only going to work with S and P shells. An S shell is just a ball. It's a sphere. Remember that this ball, even though it looks two-dimensional, it's actually a three-dimensional ball. So the first energy level contains an S shell, and this S shell is just an imaginary area, but that area is an area where there's a high probability of finding an electron around the nucleus, which is right in the center. So what this shell and its shape mean is that an electron will have a high probability of existing within this shape. The highest probability of the electron's position is depicted by the more concentrated dots, and a lower probability by the less concentrated dots. Right in the center where all the axes meet is where your nucleus exists. So in reality, the first energy level contains an S shell. That S shell can hold 1 or 2 electrons, a maximum of 2 electrons. So hydrogen will hold 1 electron and helium will hold 2 electrons within this shape, where there's a higher probability of finding an electron in the more concentrated parts. Another important thing to know is that an S shell contains 1 orbital, and 1 orbital can hold 2 electrons. Remember that we said that in the first energy level, a maximum of 2 electrons can be held. Those 2 electrons are held in the electron orbital of the S shell. So an S shell holds a maximum of 2 electrons. N equals 1 contains 1 S shell, and therefore N equals 1 can hold a maximum of 2 electrons. A P shell, well, the shell again is just an area where there's a high probability of finding an electron, but the P shell has a different shape. So the shape within which there's a high probability of finding an electron is not a sphere. It looks like an 8 or an infinity sign. Now, a P shell always comes in a set of 3. There's an orientation along the X, an orientation along the Y, and a 3-dimensional orientation along the Z. Each one of these holds an orbital. So 1 orbital here, 1 orbital here, 1 orbital here. Each orbital holds a maximum of 2 electrons. Therefore, a P shell can hold a maximum of how many electrons? 2, 4, 6. Again, an S shell can hold a maximum of 2 electrons. Every P shell comes in a set of 3, so every P shell can hold a maximum of 6 electrons. So again, let's look at the shape of a P shell. Similar to an S shell, it's just an area where there's a high probability of finding an electron, with the more concentrated dots being a higher probability area of finding an electron relative to areas of less concentrated dots. Each P orientation, as I already mentioned, has 1 electron orbital. each orbital can hold a maximum of 2 electrons. 2 electrons times the 3 different p orientations allows a p shell to hold a maximum of 6 electrons. Now, each energy level has specific shells associated with it. The first energy level, n equals 1, has an S shell associated with it. We call it a 1s shell because it is an S shell in the first energy level, and that can hold a maximum of 2 electrons. In the second energy level, we have an S shell and a P shell. We call it a 2s and we call it a 2p because it's in the second energy level. This S shell can hold 2 electrons, and the P shell, which has got 3 different P orientations in it, can hold 6. 6 plus 2 is 8. Therefore, the second energy level can hold a maximum of 8 electrons. The exact same thing applies to the third energy level. It has an S shell and a P shell. We call it 3s and 3p because it is in the third energy level. The S shell can hold 2 electrons. The P shell can hold 6. 6 plus 2 makes 8. A maximum of 8 electrons can be held by the third energy level. And lastly, the fourth energy level, as we said, can hold a maximum of 18 electrons. It has an S shell, it has a P shell, and it has a D shell. But we're only ending at the S shell of the fourth energy level. So we're only going to consider the first 2 electrons that can be held by the fourth energy level. But the fourth energy level can hold up to 18. Right, so let's go through that again. Each energy level has specific shells associated with it. N equals 1 has a 1s shell and it can hold a maximum of 2 electrons. N equals 2 has a 2s shell, which can hold 2 electrons, and a 2p shell, which can hold 6 electrons, meaning a total of 8 electrons. N equals 3 has an S and a P shell. The S shell can hold 2, the P shell can hold 6, meaning that it can hold a total of 8 electrons. And N equals 4 has a 4s shell that can hold 2 electrons. We're not concerned about the rest of the structure of the fourth energy level. We're only looking at the 4s shell, meaning the S shell in the fourth energy level. There's a very, very useful visual video on shell shapes because it is very, very confusing to understand what all these orbitals and shells mean and the high probability of finding an electron in that region. So just to help you visualize what we're talking about.